Right, so it's Thursday, which means you've got an assignment due today, or tomorrow if you take a late day. We're just about through grading PS1, so those grades ought to come out pretty soon. Average is pretty high on that. There will be an opportunity if you think, as always, if we flat out made a mistake, we're always happy to correct mistakes. But if you think that you lost, the number of points you lost is out of proportion to the severity of the mistake you made when we tested it, you can fix your mistake and ask us to regrade it, as I mentioned before. And so when we release PS1, there will be an assignment will come up called PS1R, the regrade. You don't have to do that. Hopefully most of you won't, but that's the regrade mechanism. So you'll see what that's like once we get the grades released. And PS3 will come out tomorrow and on the go. Any questions or problems? PS2 going okay? Okay. A few things I want to talk about today. I want to finish talking about testing. So you had the lab on testing, and you're coping with testing right now. In PS3, testing will be a definite part of the assignment. Part of your grade will be based on your testing. And often what we do is probably be this way in PS3, we ask you to create test cases that get effectively 100% code coverage on your code, and then we make sure you did that as part of our grading. So last time we talked about the difference between black box and white box testing. So what was the difference? What's the key difference between black box testing and white box testing? Yes?
Black box is purely to fit specific specifications. White box is as you adapt it to fit your code. Like if you're trying to get 100% code coverage, you'll write white box methods that basically will be able to hit all your different code.
Okay. So what he said was black box testing is entirely specification based. You can write black box tests before there's anything more than an interface defined. You don't look at the internal implementation, any of the internal details. You're just testing that the program adheres to the specifications. White box testing, in addition, you take into consideration the code itself. So a good example is if you want 100% code coverage, that by definition is white box testing, because you've got to look at the code you're testing to figure out how to exercise every line of code in there. So what we'll be doing when we grade your assignments is what? Black box test or white box test? Our grading test that we grade. Those are black box tests, because we don't, it's got to work for everyone's using the same specification. And then what you're doing are white box tests. Now, in either one, you talk about edge cases or corner cases, and that's just a boundary condition. Like if the method says it does one thing if the number is positive and another thing if the number is 0 or negative, then you probably ought to test for 0 or for a small positive number, because there's a discontinuity, a place where there's a change. That's an edge or a corner in the specification. So that's a place where bugs are often hang out. And when we use the term cover, that means when we say that these tests cover the code in some way, or cover the specification, it means they deal with all aspects of it. So black box tests should cover the specification. So they should test all aspects of the specification, and where you should look for edge and corner cases is in the specification. So the specification is going to say, do this if it's greater than 2, this if it's less than 2. White box testing should cover the implementation. And there you're looking for edge cases in the implementation, like conditionals and loops, places where decisions are made. But in either case, you're trying to cover. We've got a tool to cover how well white box tests cover the implementation. We don't really have a tool for specifications. We just sort of go do that by inspection. So here's we talked about this, I guess. Let's think about a black box test of a find method that does a binary search, essentially. What would be, what would it take to cover the specification here? What kind of test would you write? Yeah.
We can check to make sure the one of the items that is on the list returns true when the same item is.
Okay, so we want to make sure that when you look up something in the list, you get the right index back. Okay. What else to cover the specification? Yeah. Okay. It says what? It's supposed to return a negative number of some kind when it's not in the list, so we need to make sure that works. Yeah.
You could run a test covering if the list is not ordered.
Okay, he said, should you write, he proposed writing tests to see if the list is, what happens when the list is not ordered, but the specification requires that it be ordered. So it really, the specification doesn't say what should happen if the list isn't ordered. So we won't worry about that, because we can't really write a test for that, since the specification is undefined.
You can make one if the list is empty.
Okay, we could make sure things work correctly when you look up something in an empty list. That's an obvious kind of corner, yeah?
Just the list isn't altered as such?
Okay, that's a nice observation. You don't expect the find method to modify that list while it's searching it. And in fact, it doesn't explicitly say that in the specification. I suppose it should. It's just, I guess it's just an assumption that it would happen. So one good test would be to make sure the list isn't modified. So you could take every test that you wrote, and at the end, you could also, of each of those tests, just test that, and the list wasn't modified while the program ran. Yeah?
You can check if it exits correctly, so if it's not a list, it's correctly returned when it's not a list.
Well, if it's not a list, you know, you won't be able to call a method, so.
Well, it says, like, if it's not a list, returns that, it says to return something, so to just make sure that it is.
Okay.
And add on just a couple different things.
Okay. Yeah?
We can test for the find algorithm used, right? Maybe and or then some.
Well, okay, the specification doesn't say that it uses binary search. But if it did, I guess we could test to make sure that time it and see if it looks like it's a logarithmic curve. I've never thought to write a test like that. But if there is a performance guarantee in the specification, that is something you would test. Okay, so those are black box tests. And at the end of class last time, I was almost finished with writing a method that just generates a really long array. I think I had it containing a bunch of odd numbers, and it searched for all those odd numbers and make sure the right thing came back. And also searched for all the even numbers to make sure the right thing came back. So testing every single possible place where a number could be or could be missing in the list. It's sort of a stress test. And I wrote that test of size 100,000, but you could imagine having several tests, one that use different sizes. So those are all examples of black box tests, and I've got a list here which we pretty much talked about. Okay? What about white box testing? Now you've got the code. You can look at the code. So how do you make sure you cover all the code? What kind of test would you write here? Yeah?
Can't we use the one you showed us last time?
The one I showed you last time that I just talked about with the 100,000 elements, you give it a long list, it looks up every single thing in the list, and you give it something that's not in the list, it ends up giving you a whole bunch of things that aren't in the list that, if they were to be stored in the list, would be stored in different places. And in fact, if you ran that, it would cover this code. That's completely comprehensive. It's not always that easy to cover all the code, or to cover all the code with one test. But, and I showed you last time, we wrote like one simple test, and it covered most of the code, but there were some conditions that weren't executed, because they just didn't apply to the test that I chose. But you really want to give the code a workout. Now this is, you can look at that later if you're interested. Now it's one thing to execute every line of code. It would be better if we could execute every possible path through the code. So imagine if every time some piece of code was executed, it played a unique tone. So when I say all possible paths through the code, I mean every possible sequence of tones you could hear when you ran the program. Okay? So some of them sometimes might get longer tones than others, right? Longer sequences than others. It may find it right away, and then there's just a few tones played. You may end up you know, you're going around the loop, and maybe for a while you're always taking this branch. Not that one, this branch here. And so you get the same tone, 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 and then the tone changes. Or maybe it's hopping back and forth. So you can imagine trying to write a test case that would cause all possible sequences of tones to be played. Yeah?
There was a TA in 2420 that showed me in clips, there was a way you could like highlight all the code that hasn't been tested in red and all the code that is tested in green. It gives you a percentage.
Yeah.
Is
So,
there something
yeah, we showed that last time. So if you pull down the test menu in Visual Studio, there's a code coverage tool. And I think you looked at the lab yesterday. Yeah?
Testing coverage doesn't actually mean testing all paths, is that correct?
Right. It means every line of code was executed. So is it practical to, instead of having code coverage, have path coverage? Cover every single path. Is what? Probably not.
Not practical to have every single path covered.
Okay? And so he said it's not practical, and in fact, it's, in a sense, it's almost impossible, because what's the longest path that you could take through this program? What's that depend on?
Size of the list.
Size of the list. And so if you have a fixed size of the list you're searching, yeah, you could do all that. And I think I figured out it was, for a list of size n, there are 2 to the n plus 1 paths that you could take through there. But then that's just for list of size n. And so then what happens if there's one more element? And, you know, you can make a good argument that if you're executing every path for a list of a given length, which you will be, by the way, if you use that code I was writing at the end last time, and n is huge, and you look at the code and it doesn't look particularly tricky, you ought to be pretty confident that it works. But as code gets more and more complicated, it's, you know, it's hard to argue you've examined at least all the important paths through the code, or you've done a reasonable job of doing it. It's just really hard, essentially impossible. So it's just not going to happen. All right, now I keep mentioning that we need to test edge and corner cases. I mean, those are just synonyms. But why? These are some reasons why it's important to do that. So if you do a job of testing and you found some mistakes, the ones that you haven't found are more likely to be in the paths you didn't test. And those tend to be, you know, edge cases, corner cases, whatever you want to call them. So you may convince yourself that, oh, this code is never executed, or it's executed very rarely. And if that means it's not tested, then you shouldn't be surprised when a bug crops up there. So that's why a code coverage tool can really help, because it forces you to pay attention to code that you may not be worried about or think about. Now, when we talk about whitebox testing, blackbox testing, we're talking in terms of unit testing. So unit is just the smallest piece of code that you know, a small piece of code that you can test in isolation. So in the case for your current assignment, what's the unit that you're testing? Well, is a constructor a unit that you test? It'd be a class. You can't really test a constructor in isolation. Now, a static method can be a unit. So you can test the binary search method as a unit and, you know, with a set of tests. But why can't you really test a constructor? Why can't you test the formula constructor in isolation as a single unit? Yeah?
Because you can't call the constructor by itself, it has to be within a class.
Well, you certainly need the class to call the constructor. But suppose you have the implementation and you just want to see, does the constructor work? Yeah?
It doesn't return anything either.
It doesn't refer to anything?
Return.
Okay, right, it doesn't return anything. It may throw an exception, you can test for that, yeah?
Yeah, I was going to say exceptions, or you just don't really know if what you tried to implement in your constructor works without like going through a method or something.
Right, so in a class that's providing a new type of data, you don't test the methods in isolation. You typically, if you want to find out if the class works, like the formula class, what do? What does that test look like? You use the constructor to create a formula, and then you call the evaluate method to see if it evaluated correctly. You certainly can't test evaluate without running the constructor. And you can't find out much about the constructor without using evaluate. So the unit there is the class. And you're sort of testing things at the same time. And you may get a bug, you may find a mistake, and the test case fails. It's not even clear without some study whether the problem was in the constructor or one of the methods. They've got to cooperate to do the right thing. And if the cooperation is off, you get errors. So that's unit testing. Now, for the spreadsheet project, this week you're doing formula class. And you can see how that's connected to a spreadsheet, I guess. When you can put formulas into cells of a spreadsheet. Next week you'll be implementing a graph class. A class that keeps track of relationships, of dependencies between things. And that's a core piece of a spreadsheet because cells have dependencies on each other. Cells depend on each other, and it has to be kept track of. And then eventually, you'll end up with a spreadsheet implementation that contains the formula class and the graph class, dependency graph class. When you go test the spreadsheet class, which uses these other two classes, what is the unit then? What is the unit you're testing? Yeah.
Formula and the graph class.
Well, it's going to be, the unit you're testing is going to be the spreadsheet class with, that includes the DLLs from the formula and the direct dependency graph class. So how do you know when you find a bug in the spreadsheet that it's really in the spreadsheet, but not in the formula class? Yeah?
Unit testing on formula class?
The idea is you test the formula class to death this week and get really confident in it, and you test the dependency graph really a lot next week. And we run our grading tests on it, and then you fix those bugs. Hopefully, that code works then. You sort of trust that code so that when you combine it with your spreadsheet class and you find a bug, you can rule out that the problem is in the formula class or dependency graph class. So the idea behind unit testing, the units can get bigger up to a point. You just want to test the simplest components first, gain confidence in them before you integrate them into larger components. So that's sort of the approach we'll be taking. Now, as far as testing goes, testing should be automated. Because if it's hard at all to do, you won't do it. So, I know a lot of students that want to test by writing a main. And what they'll do is they'll write a main method, and maybe they'll call some code and print out the result. Call some code, print out the result. Maybe do that 10 times. And they want to test it, they run their main method, and they look at what's printed out and make sure it's right. And that works the first time. But what happens the 10th time? Yeah, you're tired of this. You run it and you see stuff was printed out. It was right last time, I'm sure it's right this time. It's just too hard to verify it was right. On the other hand, if you took that same code, packaged them as unit tests, and run it just by clicking a button in Visual Studio, and you either get green or red, that's not too hard to recognize what's going on. I mean, the hard part's producing the tests. So if you're going to produce the test, you might as well package them in a way that you can run it with a click of a mouse and have them automatically judged for you. Even better is when they're automatically run for you, so you can't even avoid that. So testing needs to be automated. As we said last time, testing should serve a diagnostic purpose. When you fail a test, you should be able to know what part of the test went wrong. So if you have a honking big test that gathers a whole bunch of data and then makes a single assertion at the end, and you fail that assertion, that doesn't really help you in finding the problem. What you want to do is either have a lot of simple test cases or a bigger one that makes lots of assertions, so that the assertions are pretty straightforward. So when you fail one, you know what went wrong. So design in that way. All right, so when you're done with your formula class, you're certainly not going to throw your code away. Should you throw your test code away? No, that's just part of the delivered product. The test cases are just as important as the rest of the code, so you want to keep it so that you can do regression testing later, because I will probably ask you in the future to change something about your formula class, add something to it, or change the way something works in there. And it's nice to have the test cases used before as a starting point. How many of you ever made a serious attempt to write your test cases first? Okay? And how did that go for you? Was it a positive experience or one you wouldn't repeat? Yeah?
Kind of helped me understand the assignment.
Okay, so the common thing that I say is that doing that really helps you understand what's required of your code. Before you can write code or test cases, you've got to understand the specification. And there's no better way to understand the specification than to start writing test cases against it. You'll quickly figure out what you don't understand about it. And then you have the test cases, and you can use them all through development. You got to spend the time to write them anyway. So you might as well do it at the beginning so they can do you more good for a longer amount of time. At least write some. Obviously, there are tools to help you. And also want to point out that it's possible to use assertions not just in tests, but in the program itself. So like in C#, you could put there's a statement like debug.assert. And you could put an assertion in here. And when the program is running, if the assertion is tested and it's false, you get an exception. So suppose you write a code and you know that this code, some loop, and you know that the program will not work unless when the loop ends, the variable I has the same value as n. And you look at the code and you say, yeah, I'm sure that no matter how this loop ends, this assertion will be true. But your code really depends on that fact. So just assert it. Put an assertion right after the loop, asserting I is equal to n. And if it's never different, you haven't lost anything. But if it ever is, you'll be told as your program is running. Yeah?
Wouldn't this be the same as throwing an exception?
Oh yeah, I mean, what you could do instead of doing that is you could say if I is not equal to n, throw exception. But there is an advantage to doing it this way. Who knows what it is? Yeah?
We can strip down the release builds?
It gets stripped out in release builds. So that the assertion is the test is only made in debug mode. When you build a release version, the assertions are stripped out. Because you don't want your customer to see basically your debugging sections. Yeah, so those are all things that you can do. So we've been talking about unit testing, and so we know what that is. Eventually, the units get so big that you're not talking about. It's not really unit testing anymore. It starts to be called integration testing, where you're getting larger systems. It's just a matter of scale. Another kind of testing is user interface tests. Imagine testing a graphical user interface to see that it works correctly. How would you do that?
Press every button.
Press every button and see what happens? So, in other words, manually.
Yeah.
Okay, and that's a lot of what happens, but that's, imagine doing that over and over again. You wouldn't do that very often if you had to do it. So there are tools that automate the process. There's one built in Visual Studio that I think you'll see in a lab eventually, but it doesn't work very well. Essentially, you create a test case by running something that records where you click. So imagine firing up your GUI, firing up this tool, and you start clicking on boxes, and every now and then, you just use your interface, and suppose you click on a box and something pops up. You can stop what you're doing and create an assertion that says that, you assert that what's in this box is equal to what you expected. So it records all those actions, and then when you're done, you can replay them at any time. And it redoes all your clicks and retests all your assertions. So that's possible, but I've never seen it work particularly well, but it's a nice idea. Other terms you might see are acceptance tests. So that's where the client has some tests. They want to make sure the system works as they specify. System tests are the same from the point of view of a developer. And performance tests are important. Does this scale? It's one thing that your system works on your laptop, but what happens when it's deployed to the cloud? Is there going to be a bottleneck? Is it going to fail? And there are tools for testing that. Essentially, you take some test cases and you take a web application and you tell the test system, simulate the running of this at scale. You need a bunch of computers to do it. It'll simulate web traffic, so you can test something like that. So a lot of ingenuity, a lot of thought has gone into testing. I want to emphasize this. It's not the case that you build a system and then you figure out how to test it. You need to figure out how to test it before you build it. You need to think about how it's going to be tested. You need to design it to be testable. And what happens with GUI, since they're hard to test, is to make it so that the code underneath is the bulk of the system with just a thin layer of GUI on top, so that you can throw away the GUI and still test, test the underlying functionality with just standard unit tests, so that there's less to test when you actually test the GUI. I went to the local Microsoft place down in Lehigh once and asked them about how they did their job. And one thing they said that I remembered all these years is that when they develop a new system, they're not allowed to put a graphical user interface on it, even if it's supposed to have one. So they develop, they do the underlying part, sort of the methods that the graphical user interface would use. And then there's special teams that come around and add the GUI on top, just to maintain the same look and feel across the company. So it's hard enough to do graphical user interfaces and get them to all look consistent that they have special teams that do that. Okay, so those are just some thoughts about testing. It's a really crucial part that's often overlooked. Any questions I could answer before we go on? Yeah.
How often do you find yourself doing black box testing?
Well, the way I find myself doing that a lot in grading. That's where I do most of my testing, is creating test cases to use to grade you folks. And there, my goal isn't necessarily to create the world's best black box test. They've also got to be fair in some sense, right? It's got to be that, because I got to take the number of tests passed and turn that into a grade. Any other questions, or maybe you have experience with testing you want to share, or anything? Okay. Now we're going to talk about something completely different. This has to do with C# again. So you know that C# has classes, just like Java. C# also has a construct called a struct, which is a lot like a class. Now, if you programmed in C or C++, you know that they have structs in those languages, but that's just different. Those structs are different from these structs. Just they have the same name, but they're not the same thing. So let's see what the difference is. So classes define reference types, as in Java. So you're used to that. Class instances, we call objects, are when you say create a new object, it's created on the heap. And the thing that created it just holds a reference to that thing on the heap. So we've talked about that and seen it. So you never physically hold the object, you hold a reference to the object. And when you assign them, pass them around, return them, you're just copying references around. And so you can end up with two things sharing access to the same object. Structs, to a first approximation, when you define a struct, it's just like defining a class, except instead of saying class, you say struct. There's some there are other things you have to know, most of which we'll talk about, fine points. But it's the same idea. The difference is, when you create a struct, you define value types. And value types behave like primitive values in C# and in Java. So primitives in C# are examples of value types. Value types, so when you get an instance of a struct, and there's no special word for it, so I'll just call it a struct, they're stored in place without the extra level of indirection. So when you create a struct and put it in a variable, the variable contains the struct itself. It doesn't contain a reference to the struct which is on the heap. The struct is stored in place, just like an int or a double or anything would be. And so when you pass it as a parameter, assuming you're using call by value, it's copied. The whole struct is copied. You're not passing a reference anymore. You're copying the whole struct. So the first thing to know about structs is they should be small. Right? What would happen if you had a gigantic struct? Yes?
Maybe overflow.
Not necessarily overflow. What's the problem with having a large struct and passing it as a parameter? Yeah?
You'll modify the whole struct.
Well, it's not that it modifies a struct, it's that it's copied. That's expensive. So no matter how big an object, when you pass a reference somewhere, you're just copying a pointer. 64-bit value. If the struct is, 10,000 bytes, and you store it in a new variable, all 10,000 bytes are copied to the new place. When you pass it as a parameter, it's copied. So you want to keep structs small. Yeah.
If the point of it is to save space, there's also less bang for your buck, where it's like you went from, something small, you went from saving, you're basically cutting it down by half. But if it's 10,000 bytes, you're like, cool, I've used 10,000 bytes instead of 10,008 bytes.
Right. So what he's saying is there's space overhead on an object, extra memory beyond the size of the instance variables. And you save that space when you use structs. But if your structs are gigantic, what's the big deal about saving 8 bytes or something? But if they're small, it can make a big difference. So structs exist to give you an engineering choice. And we'll look at the trade-offs as we go along. But basically, it gives you the flexibility to decide, do I want things allocated in place, or do I want them allocated on the heap and have access them indirectly via reference? So it'll make more sense when you see how it all works. So here, what I have is a class defined at the top there, class R, and you can see that it has the properties name, age, and weight. And then I have a struct V, has the same properties, name, age, and weight. So I have two new types, R and V. One is the reference type R, which is defined with the class. The other is a value type V. And then I have my method F that creates a new V and a new R, and then does a couple of assignments. So look at the picture here. Here's our stack diagram. Here's V1. So I said, new V, Jill, 35130. So it has a constructor, just like a class. But when it's created, the variable V1 doesn't contain a reference to something on the heap. It contains the actual struct here. See the difference? V1 takes up all this space on the stack. But when I create an object of a class, what's stored on the stack, in this case, is just a reference to the object on the heap. Now, what happens when I do this assignment right here? This should say R1, by the way.
Points to the heap object.
Right? So when I take R1's value and store it in R2, I copy this reference and store it there. So now I have sharing. I have two references to the same object. On the other hand, when I do V2 gets V1, again, I'm copying the contents of V1, which isn't a reference now. It's actually the object, and putting it up here, putting it here in the yellow. So it's stored in place. So why bother? Yep.
For speed,
Okay, for speed. It looks like copying is slower than doing this, though.
for accessing should be faster.
Yeah.
I don't know specifically, but if we had like a struct that we put on the stack that was huge, it would probably make it run slower because it'd have to go through a lot of unnecessary stuff to get maybe taken off.
Okay. So if you have huge structs, which you really shouldn't, and you're doing that kind of assignment where you're passing them a value, they're being copied, that's not a good idea. You can have huge structs that you pass by reference, though. Yeah?
You might have, you might want to make a copy of the object and actually modify the copy, but keep the original the same.
Okay, sometimes you may not want sharing. Right? If I do this, I really have a copy of the object, and if I go modify it, it's modified down here, and sometimes that's what you want. On the other hand, what will happen if I modify V2? I say V2.name gets Jack. It'll change this guy, but not this one, because they're not the same struct anymore. But the answer is we use structs to avoid wasting memory. So look at the object. What's the overhead of creating an object? Okay? The struct here stores a string and 2 integers. The object takes the same space, but it also has to carry around a reference to its class. So every object you create has this additional reference, this additional pointer stored in the object that refers to information about its class. That's needed because of inheritance. That's needed because of typecasting. It's needed because of the way that method calls work under inheritance. Yeah?
Are structs implicitly created on memory contiguously?
Yeah, structs are created on memory contiguously in place, not indirectly. So for every object you create, you've got this overhead of this pointer. Also, there's the overhead of this reference. So if I want a single object, okay, there's the space that's needed for just the properties, which we pay for over here. There's also this reference and this reference. Furthermore, if I wanted to use the struct, I just go here and use it. If I want to use the object, I got to follow the reference. So imagine you wanted to add a class, a complex number class, define a complex number class. What instance variables would you have? What properties would this thing have? A single complex number, what would it need internally? Yeah?
It would need 2 portions of real
Right.
value and a
So
imaginary value.
2 doubles, the real part and the imaginary part. And so the representation would be of a struct that did complex numbers would be 2 doubles big. How big would the object be if you made it a class instead? You're still going to have the same 2 doubles plus, so the doubles are 64 bits each, plus a 64-bit reference, plus a 64-bit reference. So it's twice as much memory. And that's not a big deal if you're only using a few complex numbers. But I think you would notice a difference that you woke up tomorrow and they said ints are no longer 32 bits or 64 bits. From now on, they'll be 128 bits. They're programs that will start consuming massive amounts of memory, twice as much memory. Because you don't use one complex number. You're creating complex numbers all the time. So the idea behind structs is to allow the programmer, in certain instances, which typically is when you have small objects that never change. So complex numbers, you never modify the real imaginary part. You create new numbers that are different. You don't modify an old one. So if you have an immutable thing that's small, that's the use case for a struct. Just to save all the overhead of an object. Yeah?
Will it take lesser time to access a stack compared to B?
Say it one more time.
Does it take lesser time to access
Oh.
a stack compared to B?
Well, it doesn't, if you know an address, it doesn't take any longer to go to the stack or go to the heap. But what usually happens with an object is you have an address on the stack where you find another address and you got to follow that address and then you're here. Also, when you call a method on an object, this is what you have to do. You have to go find the object, then you have to follow this reference to go find the method. And then you call the method on the object. So it's not just space overhead, it's execution overhead as well. Yeah.
There were separate locations for the heap and the stack, which I don't know if that's common. Wouldn't it make more sense to just have more easy access to the stack, make that a faster connection?
Well, I guess if you had some memory design where there were parts, well, for example, memory is like that. They're caches, right? So you got the relatively slow RAM compared to the fast cache. When your program is running, the parts of the memory that you use a lot get into the cache. And what's going to get into the cache is like the current stack frame is going to be in the cache. And the code you're running is going to be in the cache. And caches work better when lots of things you're executing, you're accessing are in the same close to proximity of memory, which stack frame has. That's a problem that the heap doesn't. So structs are for the times when you really need to do some engineering, and essentially you use structs when you're adding new kinds of primitives to the language, complex numbers, rational numbers, vectors, whatever, small things that are immutable. Okay, so this just summarizes what I said. Now, I want to make one more point, and then we'll take a break. a lot of students come away and what they'll say is that, I understand, structs are always stored on the stack. And that's not right. Structs are always stored in place. Now what's the distinction between storing in place versus stored on the stack? Where else could they be stored? They can certainly be on the heap, but how do they get there? Let me show you this. Same two abstractions up there, R and V. Now my method F is creating an array of two R objects, and it's creating an array of two struct objects. So you can imagine we create this array, then I don't have the code here because it's just, I didn't have the space. It would say R sub 0 gets new R, R sub 1 gets, peeps sub 0 gets new R, peeps sub 1 gets new R, and so on. What will it look like? What will be stored right here on the stack for R, or for peeps, peeps 1? Right, well, what will be in this box? A reference to what? Well, careful. What's it a reference to? Yeah?
Be a reference to the list of objects in the heap.
It would be a reference to an array, which in our case is two objects. What will the array contain? The two objects? References to the two objects. So it looks like this. This is so it refers to an array. Array is an object. So there's your array. The array contains references to these objects. And those objects contain references to their class. So that's what you're really doing. That's just the way Java works, the way C# works if you stay away from structs. How will the picture look different when I look at what's stored right there? What will be stored in this space in the case of peeps 2? Yeah?
Still be a reference to an array object, but the array will have the information in the array.
Okay. So what he said was, this is still an array. An array is still an object, and objects are stored on a heap. So this will be a reference to a two-element array. The difference is what the array contains. Here it contained references to objects. But in this situation, structs are not stored indirectly. They are stored in place. So where will the structs be stored? Yeah? In the array. So that's the picture. So in this case, you end up with an array of two structs, and they're just stored there. They're not stored indirectly. So you can have an object that has an instance variable that holds a struct. So you'd have an object on the heap, like this, and one of its values, or in fact 37 and 130 are essentially just like, they're value types like structs. They're stored in place. They're not stored indirectly. Now, strings are objects, so what's misleading about all these pictures here? How should I really have drawn these strings? Yeah?
Would they be pointing to a reference of the string?
What should be here, in all these places where there's strings, there ought to be a reference to a string object. But it gets too busy after a while, so I didn't do that. So a struct can contain references to objects. And an object, such as this array, can contain structs in place. So structs are stored wherever they're needed, but they're stored in place. And if an object were in the same spot, there'd be a reference there instead. Yeah?
So would the strings contain reference to the characters?
Okay, he asked, would the strings contain references to characters? No, because why? Because characters are value types. Yep.
Is it more practical to use only primitives in structs then?
I wouldn't say so. He's asking, is it more practical to only use primitives in structs? Typically that's what happens, is you define new structs to contain other value types. But I can see storing a string in a struct like I did here. Yeah?
If you created another R object with the same name as like Jack, would it point to the same string as the prior?
Okay, so if I created a new array of length 2 and I added the same two objects, I didn't create new ones, I just took the objects out of peeps 1 and stored them into peeps 3. What would my picture look like? Here would be peeps 3. Where would the references go? They go to Jack and to Jill, assuming I didn't call the constructor again and create different objects. On the other hand, what would happen if I created peeps 4 and copied the thing, took these structs and stored copies into P4? What would P4 look like? It'd look just like this, except it'd be a separate chunk. So it'd be completely separate from this. There'd be no sharing. So when you pass a struct as a parameter, it's copied up to the method. When you return it, it's copied down. When you assign a struct, it's copied from wherever it is to wherever it has to go. So it's always copied. That's why you want them to be small. And why do you want them to not be mutable, to be unchangeable? Why is it kind of weird if you can modify a struct? Imagine if you had a set class that was a struct instead. So you pass it to a parameter, you pass it to a method, that method adds some things to the set and then returns. But the copy is modified, not the original. There's no point to the method call. Yeah?
It might leave gaps in the stack, or you have to resize the stack.
Well, it's not so much gaps in the stack. It's just that a lot of times a data structure that can be modified isn't compatible with a data structure that's copied every time you do anything with it. Because if you end up modifying the copy, not the original that you care about. So you just got to be aware of that. Yeah?
Are there issues with garbage collection then?
Issues with garbage collection? Well, no more than there are issues with garbage collecting integers. Garbage collection just concerns itself with these references. All right, let's take a break and then I'll illustrate this. Okay, so just quickly, here's the fine print with structs. Classes you can define via inheritance. Structs you can't. That's to avoid the space overhead, and also the time overhead of using overridden methods. Okay? When you declare an object variable, you do not have to initialize it. When you have a struct variable, or, a variable of the value type, it has to be initialized with the default value. And by default value, essentially what it means is every field is set to whatever, every value field. So if the struct is going to have some fields, properties, whatever. So anything that's a value type is initialized to its default value, whatever that is, and all references to objects are null. Classes can have a zero-argument constructor, structs cannot. The zero-argument constructor for structs is generated for you, and it does what I said right here. It zeroes everything out, basically. So, okay, the default definition of equality is different. So when you declare two objects, the default notion of equality is reference equality. Are the two references the same? Whereas with structs, the test is made to see if you've got two structs with some fields. The corresponding fields are tested for equality by default. And we know that this, in an object method, this refers to the object on which the method was invoked. In a struct method, this is a ref parameter that refers to the struct in which the method was invoked. So the struct is sitting in a stack frame somewhere, let's say, and you invoked a method on it. In the method you're calling, you'll be able to refer to the original object as this, where this behaves like a reference parameter. Anyway, those are fine points. What I want to get at is sort of the larger implications. So I want to do a little bit more work with this model just to make sure that if you understand what I'm about to do, you have a good understanding of what structs are all about. So we have those two familiar structs, R and V, there. I've created an array that contains 7391. So that's an object. We've got a reference to it. Int 10, that's a value type, so it's stored in the stack. I create the struct Jill, 35130. That's a value type. It's stored in place. And then I've got R, which refers to this object. And I've suppressed the other pointer that goes to the class definition, just to keep the diagram a little more simple. Then we're about to call G. So in all the examples, we got some setup, and then we're about to call G. So let's see if you can predict what's going to happen. So there's G. All it does is take a parameter and set it to 20. So what's the next picture going to look like? What's the stack frame for G going to look like? Well, we're not passing it by reference. What will be in the stack frame? What's going to be stored in the stack frame for G? Yes?
Just 10.
Well, the space for M is what it is. So this red thing is just to separate the stack frames. So remember, you end up with an entry in the stack frame for every parameter and local variable the method holds. So you end up with a place to store M that holds 10. And then, when we set M to 20, and then when we return, so that's what happens when you pass a value type by value. It's copied, and then and the variable is modified up there. When it returns, there was no change to the 10 here. Right? So we're in this situation. 20 and 10 are just completely separate places. So you change the value type, it doesn't affect anything down here. Now, what happens if G takes its parameter by reference? So now we're passing a value type, namely an int, by reference. What's the picture going to look like now? There'll still be the same one entry in the stack frame for M, but what will be the initial value of M? Yeah?
A pointer to N.
Right. So what's actually this green thing, this green pointer, this green reference, just says, well, when you need to use M, come down here. So when we say set M to 20, you're actually modifying down here. And when you return, N is changed. And we've seen that before. That's just called by reference. Okay. What happens when we pass A sub 1 by reference? So A sub 1 is right here. We're passing it by reference to that same G up there. What's it going to look like?
Reference to the location and where.
We'll get a reference stored, and the reference will point where? Right there. Okay, so you can pass that by reference, and when we set in the 20, we're actually changing the array to 20 there. And then when the method returns, the array has been changed, because we passed by reference. Okay, so here what I'm doing is I'm passing R. So R is an object, reference type. So here's R. We're going to pass it to G, which is expecting an R. So the stack frame for G now is still just going to have the one entry, because it's only one variable. What will its initial value be? What will the initial value of S be? Now we're passing a reference thing, not a value thing. What will be stored in the stack, in S in the stack? Reference to what?
R.
Right, a reference to this thing right here. Okay, that's just passing it by value. So then when we change its name to John, what happens when we change S? We say S gets new R. What changes? We create a completely new object, right? And so S will now refer to it. Doesn't change this reference. Then when we return, that new object goes away with the stack frame. Okay. Now, same setup, we're passing V, a struct. We're passing this thing here by value. What's my stack frame going to look like?
3 frames.
Well, no, there's just one frame. When you call this method, there's one frame. How many variables will be stored in the frame? Depends on your point of view. Just one. And what will that variable contain? Struct. So, just like when you pass a reference by value, the reference is copied here. When you pass a struct by value, it's just copied up. So that's an expensive operation to pass a struct by value. So all this stuff is copied up. Now, when we change W, so this is W now, we change its name to John, that changes. We're just changing the copy. What happens when we say W gets new V? We create a whole new struct. Where does it go?
In place?
In the same place it is now. We're just replacing this with a new struct, right? So whatever it is goes there. It's just like assigning a new int to a location. In this case, it's a bigger thing. Then we return and all that goes away. So you see what's coming up next. We're going to pass the value type by reference. So we're passing this thing, this struct, by reference to G. So again, there will be one entry on in the stack frame to store S. What will S contain? A reference to this spot down here. Oh, wait. Okay, I'm wrong. We're passing the object by reference, not the struct, I'm sorry. So R is this object. When we pass it by reference, we end up a reference to the place where the reference is stored. So now if we say s.name goes to John, we follow the green pointer here, then we follow this reference out here and change that to John. And when we say s gets a whole new object, what's going to happen? We create a new object with a reference to it. Will the reference be stored here, or will it be stored here? Second one. The green references are different from the red references. Green just says, if you want to store something in this variable, follow this, and that's where you really store it. So you get that picture. So that when you return, you've got a new thing there. Okay? Now we get call by reference with a struct. Going to be the same picture. We're going to have a W up here with a green arrow in it. Where will the green arrow point? To the original struct. So it's not really pointing to 35. Think of this pointing to this whole variable here, which contains a struct. Again, when we change name to John, that gets changed. And what happens when we say W gets a whole new V? You know, we want to store it here, but there's a green arrow, so we come down here and we store it right here instead. So we get that. So that shows you the way that what we're crossing here is reference types and value types, namely R and V, and how they're passed as parameters in the presence of call by value and call by reference. And you see different effects taking place. There's similarities and there are differences. So if you understand that, you got a good understanding of how structs work. If you don't understand that, you need to ask questions or go through these slides till you can predict what's going on, because it's not arbitrary or random. It makes perfect sense, but it's, you know, so you have never used structs, so it's kind of an academic concept right now. So, take any question at all, replay any slide you want. Yeah.
Is that red block just there to make it easier to look at?
Yeah.
Okay.
The red block that I put in, like right there, wouldn't really be there in a real stack. It just makes it easier for us to understand when we're standing here. Yeah.
Do we have to have the REF and the G method, or could we just, the parameter?
Okay, so the G method has a parameter, and the question is what?
Could we omit the REF?
Oh, well, if you omit the ref, then you're just going back to call by value. In which case, you wouldn't have these green arrows.
So then it's going to point in the...
Right, so if you took the ref out, there'd just be a red arrow pointing to here. Other questions? Yeah.
So passing in a struct by reference is basically the same as passing in an object in terms of how the variables are
Okay.
identified.
So what he just said was that passing in a struct by reference is the same as passing in an object by value.
In terms of like...
Okay, well, let's look at that. Let's see. Okay, so this is passing in, let me go back here. This is what it looks like when you pass in a struct by reference. So you end up with a reference to a place in memory where a struct is stored, to the stack in this case. Okay, now what if instead we had passed suppose instead we had passed this object by value, what would we have? We would not have a reference back to here. We'd have a reference directly to there. So it's the same, it's sort of the same effect in that when you call the struct by reference, you end up, referring to this chunk of memory via the green arrow. In the other case, you refer to an object via a red arrow. So you sort of got sharing set up. So I can see where your observation is coming from. It's a lot like that. You know, it's not exactly the same thing, but it's. One difference would be, if you do an assignment to W, you're changing this thing right here. If you pass an object by reference and you do an assignment, you're not affecting this at all. You're creating just a whole new reference. Other questions? Yeah.
Can you go back to the slide where it was at the very beginning when you were assigning like a class of, like when it was the direct reference, like class of R.
So passing an object
Yeah, when you were passing R into G
at by value or by reference?
by value.
Okay, let me go and I'll see it. That's a ref int. I think it's right here.
Mm-hmm.
Okay, so what we got this set up and we're about to pass R by value to G. And so what happens is, when you do call by value, you just, imagine there's some bits stored here. Right? The bits are a pointer in this case. The bits are just copied up to the new place. And you end up with two pointers to the same thing. If you pass a struct by value, again, you just copy these bits. There's more bits to copy in that case. So is there a particular question about this? I just want to see it.
I don't know how to word it correctly. So in this,
Mhm.
so you're directly acting on those, so you're copying the bits to get the memory location.
All right, so we've got two references to the same chunk of memory in the heap.
And then you can change those.
Right, so when I say something like s.name, what happens is we say, okay, S is an object, so I must follow this pointer. And now I've got to find the name field, and now I've got to change it to John.
And that'll stay
Yeah,
after you.
because I've still got a reference here. If I didn't have this reference, and when the method returned, there'd be no references from the stack to this object, it would be garbage.
Then why would you ever, like, why would you create a struct if you can do the same exact things?
Okay, so she's asking why create a struct when you can do the same things with an object? And the answer is just, it's just an engineering decision. If you're going to have, if you have small, if you can think of a primitive value you wish C# had included, like complex numbers, and they have the property that each struct is small, 2 doubles, and it's immutable. There's no method that changes the real imaginary part. That's where you use a struct, to avoid having to use twice as much memory for this object as you would for a struct. It's just it's more efficient. But there are lots of things you would never make a struct. If you're in doubt, make it an object. If your program's acceptably efficient, don't worry about it. But if you need to, sometimes you need to squeeze the last bit of efficiency out, and one way to do that is to introduce new primitives with a struct. Yep.
For the G method, is you declare the argument with the type of reference, the reference type, and then you pass in the V, right, the struct. What's going to be the output, the result?
Okay, so what you're asking about is this situation right here. We've passed V by reference. And anything we do to W, we're actually doing to this right here. So it gets changed, that gets changed, the method returns. So two completely different things. Reference types, value types, call by value, call by reference. It's a little unfortunate that both use the word reference in different ways. And you can mix them arbitrarily. Yeah.
As far as the stack and goes, is modifying like I know we have the reference, the heap, but modifying the value on the stack, is that a lot quicker? Like it
Okay. So, I mean, modifying a value in the stack versus modifying a value in the heap is the same memory operation. But typically, to modify a value on the stack, on the heap, you first got to go find a reference on the stack, and then go to another place in memory, and then do the modification. So structs let you eliminate the red pointer there. So you just go right here and change it. So that's another advantage. This level of indirection is lost. And as I mentioned, you call a method or an object. To find the method, you've got to follow a pointer to the class and find the method. So when inheritance was first invented, people objected to it because it made method calls less efficient. You had to follow a pointer to find the right method. And this is, C# is sort of a reaction to that, sort of lets you do it either way. Yeah?
Is the only benefit to pass by reference that you can pass a reference variable and create a new object with that reference? And
well, the advantage of call by, there are two advantages to call by reference. Well, there are several. One advantage is you avoid copying. And that's not important for passing reference types around because they're all just one pointer. But if you're passing bigger things like a struct as a parameter, passing it by reference allows you to avoid the copy. Okay? Passing by reference gives you a way to return more than one thing from method like we saw. It gives the method that you're calling a way to modify variables down in the other stack frame. So that's another advantage of call by reference. Okay. All right, we'll stop there and do something new on Tuesday.